Our next speaker is Dr. Azad Madni, researcher, educator, entrepreneur, and author. A distinct member of our CERC Research Council, Dr. Madni's research is cross-disciplinary and use-inspired. His specific areas of research include model-based interactive storytelling in virtual worlds, virtual reality-enabled distribution simulation for collective training and collaborative engineering, formal and probabilistic modeling in engineered resilient systems, and intelligent multi-agent planning and decision-making in autonomous systems and systems of systems.
Hello, everyone. I'm Professor Azad Madni from the University of Southern California. My presentation today is on our CERC-sponsored research that is concerned with developing an adaptive cyber-physical human systems testbed to support model-based system engineering research. The target application domain for this testbed is multi-UAV operations in missions such as maintaining physical security of and search and rescue. This problem domain within the CERC universities. The research prototype was transitioned to CERC universities, including University of Arizona, Virginia, and University of Virginia. An earlier version of the testbed was transitioned to the Aerospace Corporation, where faculty and students are now at Virginia Tech and the University of Arizona. I'll give you a brief outline of my talk today. I'll give the project's objectives and motivation. I'll share with you the approach and implementation. Then I will talk about the core capabilities of the testbed and the illustrative scenario that I just described. We will then briefly review this we have accomplished, and then I'll conclude with benefits. Other people. I'm the principal investigator. Professor Dan Irwin is the co-principal. Dr. Madni is the project manager. And my two graduate research assistants on this project are Edwin Ordokhanian and Paris Safuya, who are both PhD candidates. So, the project's objective is to develop a cyber-physical human system testbed for experimenting with different models and algorithms, demonstrating model-based system engineering innovations. For example, the use of digital twins in model-based system engineering. And finally, the position of the capabilities, models, and algorithms to target sites, which in this case happens to be specific CERC universities. As noted earlier, my domain of application in this case is unmanned aerial vehicle team operations. The motivation for this project stemmed from a discussion a few years ago with the CERC executive director. And what the motivation was is to enable CERC researchers working on model-based system engineering for autonomous systems to focus on research and implementation, to focus on research and experimentation and not on implementation details. The idea was to provide a convenient platform to these researchers to showcase their research products on demand and to facilitate comparison and integration and testing of virtual models and digital twins. A companion product of this research is to simplify interoperability among models produced by the CERC researchers. And finally, and perhaps most importantly, to facilitate the sharing of engineering artifacts and lessons learned. So what are cyber-physical systems? I gave a definition of this in a prior CERC review in 2018, and I'll share that with you today. Cyber-physical human systems are a class of safety-critical socio-technical systems in which interactions between physical systems and cyber elements that control its operation are influenced by human agents. The system objectives are achieved through interactions between physical systems to be controlled, the cyber elements, which are really the communication links and software, and finally the human agents who monitor and influence the cyber-physical system operation. The key distinguishing feature of cyber-physical human systems from any other man-machine system is the fact that humans can intervene at any point to redirect the cyber-physical system elements or supply needed information, not just to exercise manual override or assume full control. So the approach, very briefly, is the following. We use ontology to define testbed capability and use ontologies to integrate the components and the capabilities of the testbed. We use end-user-oriented scenario definition using graphical and scripting capabilities. We have both facilities in our testbed. We have a smart dashboard for execution, monitoring, visualization, and control of the physical assets in the simulation. Our software is all based on open source that is well maintained and low-cost commercial components. We have the ability to demonstrate this capability of the testbed using an illustrative problem scenario that we have shared with all our transition sites. We provide a starter kit and a user guide to allow users to hit the ground running and not have to go searching for material. Our transition strategy from day one was to enable smooth technology transfer, and in fact, we accomplished that. So the first thing we have is the Testbed Ontology. And here are the key elements in the Testbed Ontology. We have, excuse me, I have to go back one. Here are the core technologies of the testbed. The first is the Testbed Ontology, where we provide the basis for defining and integrating the testbed capabilities. The second key component is a scenario builder, and we have both graphical and scripting modeling capability. The third key component of the testbed is the smart dashboard that we use for monitoring, visualization, and control. This dashboard can be customized to various scenarios and is context sensitive. We define context, in this case, using the military mnemonic called METTC, which stands for Mission, Enemy, Troops, Terrain and Weather, Time Available, and Civilian. We support different system modeling tools, including SysML, decision trees, hidden Markov models, and partially observable Markov decision processes. We employ a drone kit platform, which has both visualization and low-level control facilities. The physical hardware consists of quadcopters, which is a kind of unmanned aerial vehicle, and we have a digital twin of that quadcopter created, which is a virtual model of the physical system. And then finally, we have the quadcopter planning and decision-making algorithms. The Testbed Ontology has several components. The first is scenario, which is basically, in simple terms, a mission specification, context for experimentation with the testbed. The second key component is world, which is the geospatial region which supports experiments. The third is vehicle. And in the work that we have proposed and the work that we have done, we are using a quadcopter, which is a type of unmanned aerial vehicle, for our experimentation. The next key term is agent, which is an active element which may or may not be a vehicle. The next key term is experiment, which is a scientific procedure to test a hypothesis or to demonstrate a capability. The next key component of the Testbed Ontology is laboratory, which are elements that are used in experiments, and they Wi-Fi. The next the ontology is a project. This needs to be provide benefits. And the next key component is scenario builder, which facilitates the creation and modification of scenarios. The smart dashboard, of course, visualize, monitor, control, and also to import scenarios from third-party applications. The standard vehicle in this case is a physical quadcopter, and the predefined scenarios that we have in our Testbed Ontology are basically a starter kit to get users quickly up and running the testbed. We have which is software to collect simulation execution data, and then we have a digital twin, which is the software replica of a physical system. And this software replica also includes the history of the system, which means it's a particular physical generic type of system. Here you see the testbed architecture. This is the transition and delivered to the various universities. The key components are system modeling tools that you see on the top left corner, a user interface that you see below that for scenario building, a scenario-driven dashboard, and report generation facilities. In the center, you see a private cloud to provide requisite protection of model-based system engineering assets. And of course, that's connected to a repository, which persistently stores model-based system engineering knowledge assets. Below the private cloud, you see the simulation engine, which is used to support model-based system engineering experimentation. Here you see the testbed hardware. To the left is in two different sizes. In the middle is a quadcopter controller, which has 3 programs that can be defined by the user. For example, hold, hug. We also have a fully automatic mode, as well as an altitude-only mode. To the right, you see the dashboard that comes with the Ardu pilot. The dashboard that comes with this system, hardware, is used to calibrate the flight controller, calibrate the remote controller, and watch the current status of the quadcopter. The test capabilities, we offer a scenario builder to model and import scenarios from third-party applications. The testbed monitoring, visualization, and control of the simulation. We have a digital twin capability that we can create and use in-system simulation. We have the ability to control both the physical vehicle, which in this case is a quadcopter, as well as a virtual model of the quadcopter. The data collection capability is based on the vehicle-mounted sensors that is used for post-hoc analysis. And we have the ability to capture the execution trace, which is the scenario execution audit trail, which is displayed on the dashboard. The standard vehicle in this case is the physical quadcopter model. It's a pretty clean, simple design, which has ease of assembly, crashworthiness, which means it can crash without damage. And this is something, a lesson we learned. We need to have something that was fairly robust to crashes as we were experimenting with it. We have a software that employs a discoverability component, which automates the vehicle network communication. It provides a plug-and-play capability, and the manual setup of vehicles using IP addresses is no longer needed with this capability. The smart dashboard is scenario-driven. Importantly, it allows users to import scenarios. It's context-sensitive. Its layout is customizable. You can lay out the various panes on the dashboard according to your needs. It provides a default display option that gives you a plan view, which is also called the mission view of the world, showing the vehicles in that particular terrain. It has various camera views. It has vehicle state indicators, and it has resource state indicators. It has the ability to accommodate human intervention. And when humans do intervene, they do so to either retask vehicles or to reallocate resources. It has an audit trail display capability that shows you when vehicle states change during the execution of the mission. And of course, we have the ability in the dashboard to set up and control the experiment. So you have start-stop facilities as well in the dashboard. The testbed provides a user guide. The user guide consists of a starter kit of predefined scenarios. Here, the users can use scenarios right out of the box in a simulation environment and later in the physical laboratory. We also provide multi-vehicle control algorithms. 2 types of algorithms are provided: a rule-based model, which is a deterministic algorithm, and a partially observable Markov decision process model, which is a probabilistic algorithm. We also provide scenarios and control algorithm documentation, and that contains basically how scenarios and algorithms can be created, and how scenarios and algorithms can be modified. The scenario in our case is an aircraft perimeter security scenario. The context is that of a C-130 troop transport aircraft which has landed on an airstrip. It needs to maintain close surveillance of the aircraft perimeter. That's the challenge. The collection assets, or the sensors, if you will, are building-mounted video cameras and quadcopter drones with downward-facing cameras. So these are the two collection assets that collect the data in terms of maintaining the perimeter security of the aircraft. The goal here is to maintain video coverage of the aircraft perimeter despite disruptions. And disruptions could take the form of you could lose a drone, or you could have loss of a building camera. And of course, then you have to readjust your coverage so you can restore to the best possible way you can. The actions that you have available in this case are simple and compound. You can reposition a currently flying drone, you can launch a reserve drone, or you could do both. System states are displayed using color codes. Green means you have full coverage of the perimeter. Yellow means that you're responding to a disruption. Red means that you lack the capability to restore full coverage. And if it's red, the cyber-physical system alerts the commander to intervene. Here's a pictorial view of the scenario that I just described. And here you can see the C-130 aircraft. You can see the various UAVs that are in a reconnaissance mode in maintaining the perimeter of this aircraft. And you see this aircraft on a runway. And you can see the various camera preview and camera views that you can see here to the right in the box that you see there. So here is the actual software implementation that is part and parcel of the testbed. In this particular case, what you see is the dashboard that shows you the scenario simulation. The problem domain, again, being addressed here is the perimeter security of the stationary aircraft that you see in the left-hand mission view window. The top right window presents a selected camera view. Below the mission view, to the left, is the mission log that presents all the state changes for all the vehicles involved in the mission. Below that are status indicators of the battery level for each of the 3 vehicles involved in this particular mission. The location, velocity, and the altitude of each vehicle is shown right below the battery level indicators. To the right of the mission log are the controls, which can be human in the loop or fully automated. Once the simulation starts executing, the coverage achieved appears below the controls window. You get to see how much coverage you have. To the right of the controls window are the camera views from each of the 3 quadcopters. And from the building-mounted video cameras. So that's what you see on the right-hand left. This view, you see the dashboard that shows the coverage area. The quadcopters in this particular case have not been launched yet. So the coverage that you see here is due only to the building cameras. And that's what you see in the left. All those shadows and things like that, the coverage that you see are the building cameras and the coverage that they have achieved. And it's strictly with those static cameras that you see that coverage, because no quadcopters have been launched so far. In this screen, you have one of the quadcopters that has launched. So the quadcopter is flying. Note that the control now in the center at bottom, you see it shows automatic fitness optimization. That box is checked. And that means that the quadcopter is moving in a manner to maximize a fitness function. The coverage area here shown is the coverage due to the quadcopter now. The messages that you see in the mission log show the quadcopter search for the optimal location. A fitness function, by the way, is a particular type of objective function that is used to summarize as a single figure of merit how close a given design solution is to achieving the set of aims. So fitness functions are typically used in genetic programming and genetic algorithms to guide simulations toward optimal design solutions. We use that here to maximize coverage. Here you see the optimal location for a single quadcopter. So the quadcopter has been flying and it has found the optimal location. And in this particular case, if you look at the mission log, you see that the quadcopter has climbed 60 meters and yawed about minus 20 degrees to fit its field of view with the aircraft perimeter. Here you see the same thing, but now you have 3 quadcopters and they have their optimal location. Once again, you can see at the bottom right, you see the quadcopters, and you see in the center the coverage you achieve. And in this particular case, the coverage is much higher than the previous one because you've got 3 quadcopters, and the fitness function says it's 49.88 that you see in the center of the screen. Interestingly, you will note that the selected quadcopter has rotated in its field of view to concentrate on the east end of the perimeter in this case. That's what's happened in this particular screen. Here you see yet another view, and this is a plan view of the terrain. This view can include not only the actual, for example, the terrain and the various actors, but also any computed artifacts which can dramatically increase the ability to interpret the scene. For instance, this figure shows the terrain for the perimeter surveillance scenarios, the computed artifacts, including the viewing volumes of the camera. Those things are shown here in this overlays. It's called the nadir pointed view with perspective. The nadir is the local vertical in the direction of gravity at that location. So that gives you an idea of the kind of rich the visualizations are. I've with you just a few visualizations so far. We have many more that in the interest of time I can't present here. Our successful transitions have been to the University of Arizona, the University of Virginia, to Professor Alejandro Salado, who's now at the UFA. And the second one is, of course, to Professor Peter Bailing at Virginia Tech. And then the last one is the Aerospace Corporation to Dr. Bob Minichelli, who's head of System Engineering Division there. So now let's look at the benefits and payoffs of this testbed. It gives you easy entry into the field. You can start quickly with $0 investment by installing open source software and running pre-built simulation scenarios. We also use high volume, inexpensive consumer commercial off-the-shelf hardware. And that basically makes sure that you don't have any kind of a significant cost. The testbed is easy to assemble and replicate. It has a library of standard hardware and components, for example, a library of quadcopters of different scales. It offers identical software interfaces, which is protocols for both for the virtual model and the physical system. It reduces the risk of experimentation. So, because the experimenters can work with proven and known designs without the need to design new vehicles and become expert makers. It offloads the researchers, in this case, the CERC University principal investigators and their teams, from getting bogged down with implementation details. And it does so by providing a library of models, connectors, infrastructure for interoperability. It facilitates easy comparison. You know, you have effective visuals, which are multi-perspective, multi-level, as you've seen, and you can compare results from multiple researchers to see which one does better in what context. We have the ability to enable best practices by having rapid dissemination of extensions. Anytime we have a modification or a new system that we have created, we can disseminate that to the system engineering community. We have the ability to rapidly realize new integrated capabilities. We have the ability to do some cost-effective experimentation, for example, test models of vehicles and sensors, as well as algorithms, for example, optimization algorithms like I described, as well as machine learning algorithms like reinforcement learning. And we can test all that in simulation. It provides significant time and cost savings because we have a freely available backbone, which are the primary tools for creating experimentation environments. And as importantly, it allows the various principal investigators at these various universities to provide on-demand demonstrations to CERC customers as well as to internal customers within the university. So in summary, what you've seen here is the work that we concluded a few months ago in building a adaptive cyber-physical human system testbed with a specific focus on model-based system engineering and researchers at various universities. Our focus is on cyber-physical human systems in general. The capabilities that we have right now are end-user scenario building, a smart dashboard for scenario execution, visualization, monitoring, and control, insertion of digital twin technology to enhance verification and validation, a capability that is needed in modeling and simulation, and that's needed especially in model-based system engineering as MBSE starts to encompass more and more of the life cycle. We have the ability for instrumentation of scenarios, both on board the vehicles and in the adjacent environment, and collect data from them. And we have a library of models and connectors as part of the overall MBSE testbed. Currently, we are supporting CERT researchers in autonomous systems. I mentioned to you the two universities that are actively participating are University of Arizona and Virginia Tech. They're using it for scenario definition and system modeling. They'll be using it for what-if experimentation data collection, for creating and sharing model-based system engineering artifacts, for doing cost-effective experiments, and importantly, for continuously improving system models and refining their model-based system engineering processes. Here are some of the recent testbed publications that we have. We have published quite a few in some reputable journals, as well as in conferences held by IEEE and in COSI. And that's me. Thank you very much for your kind attention. And I hope to see you there in person. I recorded this just in case there was any hiccups or difficulty in making a personal presentation. I look forward to our virtual conference. Once again, thank you all.
I saw you already addressed one comment. There's another question here in the chat. Are you able to come onto video or hear me?
I can hear you now. I think I just got enabled.
Yep, I can hear you. So we have a question here from someone in the audience. What skills would a user need to use this framework for performance simulation or other cyber physical systems of interest?
Well, we have tried to really lower the entry curve by providing a graphical interface, by providing a starter kit, and so far what we have distributed to the other universities, students are able to pick up and run with it, and most of these students are system engineering students who have familiarity with SysML, but we don't rely on SysML here to any great degree at all. You can use whatever modeling framework that you're familiar with. So for example, in this particular case, because this is a probabilistic environment, we are using partially observable Markov decision process models in the experimentation. But because you've got these building blocks, and because you've got the kind of guidance that the testbed provides, you don't have to have a great steep learning curve. You don't have to know the details and the guts of the optimization algorithms or the guts of the machine learning algorithms to get some value out of it. So I have undergraduate students actually working with the testbed all the way up to PhD students. So I would say that given the number of people working on it, we have tried to find the sweet spot that on the one hand, we don't trivialize what we can solve, and at the same time, make the entry level as low as possible so as many people can participate who are non-programmers and mostly system engineers who are non-programmers.
Thanks so much, Azad. And they clarified a bit further. Is this model limited to UAV systems, or can we extend it to other types of cyber physical systems?
So I've actually extended this work in the world of automotive domain. My research is sponsored by autonomous vehicle companies, and I've been able to take the testbed and instantiate that for self-driving cars. And we've been able to do that quite successfully in ground vehicles. But if you were to tell me what about underwater vehicles and stuff like that, I would say no, because we don't have that kind of an environment model. But as far as air and ground vehicles are concerned, we're able to handle them. And that's what the objective was when we set out to do, was to address aerial vehicles, primarily UAVs of different types, and ground vehicles to provide some degree of, to show that there's some a transfer of technology from what we created for airborne vehicles for ground vehicles. And we were successful in doing that. Of course, with ground vehicles, you have a different set of problems. And so we had to do some additional work to make that happen. But yes, the testbed is currently supporting both air and ground systems.
Excellent. Thank you so much, Azad. And it was great to have you here.